Yes, it's my pleasure now to introduce Emanuele Dotto from University of Warwick. And the title of his talk is Hermitian K-theory of stable infinity categories. Go ahead, please.
Yeah, thank you very much for the invitation. It's a big pleasure to be here. And thanks for pushing through with the program, even despite the circumstances. In fact, Barcelona is one of my favorite cities, probably my favorite. I really hope to have a chance to visit later on for sure. So I will take this occasion, since it's a program on higher category theory, among other things, I would like to talk about this project I've been working on with all of these co-authors on Hermitian K-theory of stable infinity categories. So here we really use the power of higher category theory to study some more classical object, typically Grothendieck-bit spectra. And I would like to take it slow, start with the very basic objects, and slowly build towards our result throughout the talk. So let me mention explicitly my co-authors. This is all joint work with Kalmes, Harpaz, Hebestreit, Land, Moy, Nardin, Nikolaus, and Steinle. And we are 9 people. So I'm gonna refer to these as with the number 9, otherwise it gets too messy. Okay, so let me start with some background on Hermitian forms and on Hermitian K-theory. So section 0, some background. On forms. Right, so we started with the ring R, and I've seen, unfortunately, only attended one talk this week because of teaching and other craziness, but in that one talk, K0 of R was defined, but let me remind you what that is again. So the 0th K group of a ring R is defined as follows. We look at the finitely generated projective R modules and modulo isomorphism. And we realize that this is a monoid under direct sum of modules. So we did, the direct sum operation, so it's a monoid. And if you have a monoid, you can always group complete. So meaning formally add inverses or perform the Grothendieck construction. So this is the same procedure you do for passing from the natural numbers to the integers, for example. And this is the usual Grothendieck group or K group of R. So this is the 0th K group of R. Okay, and the idea for Grothendieck-bit theory or Hermitian K-theory is to do the same construction, but instead of just modules, consider modules equipped with a form. And there are different flavors of forms one can consider, and I will try to stress this throughout the talk, but for start, let's just look at symmetric forms. So let's try to do the same thing. And just for sake of expositions, I'm going to assume that my ring is commutative. There are versions for non-commutative rings, but it makes my life a bit easier. So suppose now that R is commutative. And let's take a finitely generated projective module, P. And then a symmetric form I should say, no, more things. So not only a finitely generated projective modules, let's also take a unit in R, unidempotent. Okay, and now I can put some adjectives in front of the word form. Let's say symmetric, it's also non-degenerate. So non-degenerate. And maybe we should say epsilon symmetric, although I'm probably not I'm gonna try not to mention this epsilon too much. And non-degenerate symmetric form on P is an R-linear map. So it's a pairing on P. It's a map of R modules like this to R, and it satisfies 2 conditions. It is, well, corresponding to the adjectives I put in front of form. It's symmetric, so this means that if you evaluate it as the tensor product of two elements in P, this is the same as evaluating it at the tensor product of the two elements the other way around, but then we pick up a twisting by this unit epsilon. And typically, I should have said that epsilon typically 1 or minus 1. And so symmetric, and it's non-degenerate. What does it mean to be non-degenerate? It means that if you look at the adjoint map from P to its dual, let's call it phi tilde maybe. Okay, so this is the dual module, that's denoted P star, and this adjoint map is an isomorphism. Okay, so this is the classical notion of a non-degenerate symmetric form. And there's a fairly straightforward notion of isomorphism between these. It's just an isomorphism of modules that respect the form. And so from these, I can construct the Grothendieck group. So the Grothendieck group, the Grothendieck group of R, and let's try to keep this epsilon in the notation, is by definition, we look at pairs now of a finitely generated projective P together with such a form. And I do exactly the same thing. I take isomorphism classes. This forms a monoid under direct sum. And again, a monoid. And I can take its group completion. Okay, this is called the Grothendieck group, or zeroth. Grothendieck group. Okay, and now, so this is really, well, let's say we want to understand this group, and let's suppose that we understand K-theory already, so that we know the K group. Can we sort of leverage the knowledge we have of K-theory to understand this one? And in other words, if you can maybe map, we can try to define a map from K-theory into this group and understand its co-kernel. So let's do that. And this also produces some examples of these symmetric forms. So there is a map called the hyperbolic map. From K naught of R into the Grothendieck group. And let's see what that does. So it takes a module, or an element in the K group, determined by a module, and it sends it to to the following. And it will give a module with a form, and the underlying module of the form is going to be the direct sum of P and P dual. And let me describe the adjoint maybe. So the adjoint is going to be a map from this module to its dual, which is P dual plus P double dual. And now it's a map between the direct sum of two modules, so I can give you the matrix of this map under this direct sum decomposition. And maybe that's some more space. So it's a matrix. The first entry is the map from P to P dual, but there's no canonical map from P to P dual. I just started with a module P, so I have to put 0. And similarly, in the other corner, there's no map from P dual to P double dual canonically, so let's put 0. But in the off-diagonal terms, there's going to be maps from, let's see, this lot up here is a map from P dual to P dual, so I can put the identity. And in the other corner, here is going to be a map from P to P double dual. And here, there is always a canonical map that sends a point to its evaluation. And this is always an isomorphism. And it's for finitely generated projective modules. And so I can put that map. And let's call it can for canonical. It's a canonical identification from P to P double dual. And then I still haven't used my epsilon. If I want this to be actually symmetric, I need to put an epsilon there too. And this is called the hyperbolic form on a module. and this gives you an analytic map like this. And now I can ask what is the co-kernel. So let's describe this algebraically. Let's see. Let me say that. Let's describe. Of the hyperbolic map. And so it's going to be some quotient of this group. And so let's start by defining a relation on this isomorphism classes of forms. And it's going to be the following relation. So a Lagrangian of a form P phi is a finitely generated projective submodule for L, such that two things happen. First, if I have a form on a module, P, I can always restrict it on a submodule. So, and I want this form to be 0. And the second one is the following. Phi provides an identification between P and the dual of P. So we saw that already. And now I can, of course, take the dual of this inclusion, and this gives you a map to the dual of L. Okay. And I want this, I mean, yes, I'm kind of ignoring this term. So I look at these three terms sequence, and I want this to be exact. Okay, this is the notion of a Lagrangian, and now I can define another group which will play the role of the co-fiber of this hyperbolic, or the co-kernel of this hyperbolic, which is called the big group. And what do? I start again from these isomorphism classes of forms as before, and I mod out by the relation, by the submonoid generated by forms that admit a Lagrangian. So I say that I declare a form to be 0 if it admits a Lagrangian. Okay. And this is a quotient in the category of it's a quotient of monoids. And this is called the big group. Of R, and it's an observation you need to make that this is in fact a group. So it's a quotient of monoids, so a priori it's only a monoid, but actually every element turns out to be invertible. And then it turns out that this sequence is exact. So you can look at the hyperbolic, and then so this is a group, and as a monoid, it receives a map from forms modular isomorphism because it's a quotient of that monoid, and so by the universal property of the group completion, there is a map to the big group, which literally sends a form to its class modular Lagrangians. And this map is surjective because it's surjective of representatives, and this sequence is exact. Okay, so this exhibits, well, up to some kernel that could show up here. This is, well, yeah, there is an exact sequence like that. And now a natural question would be, does this lift to a sequence of spectra? So we know that K naught is the zeroth homotopy group of a spectrum. It turns out that the same is true for this one. And with a bit of more work, you can show that this is also the zeroth homotopy group of a spectrum. And you can ask if this is a fiber sequence of spectra, or arises as a fiber from a fiber sequence of spectra. Point being, this will give us a chance of understanding this middle groups as an extension of the other two. So let me try to say that a bit better. So a motivated question is this. Does this. Come from a fiber sequence. Of spectra. So let me spend a bit of time talking about how to lift those two spectra. So first, let's start with K-theory, which is the one that is usually familiar. So what is the K-theory spectrum of R? The connective K-theory spectrum. One way of defining it is we try to define it. So let's look at how we define K0. We define it as this group completion of something where we kill the isomorphisms. And the idea is to keep the isomorphisms around and group complete in topological monoid instead of in discrete monoids. So let's try to do that. So instead of killing isomorphism, we keep them. What does it mean? We look at the category of finitely generated projective R modules and isomorphisms. So we don't take isomorphism classes, we regard this as a category. Then we take its classifying space. And now under direct sum, this is a monoid, and it's in fact an infinity monoid in spaces. So infinity, it's a fancy word of saying, well, it's a fancy version of commutative. Somehow it encodes in a very structured way the fact that the addition of modules is commutative. And in infinity monoid, if you are a bit careful, you can also take the group completion and get an infinity group, or a group like infinity monoid. And so this is done in infinity monoid. And this gives rise to an infinity group, aka a connective spectrum. And I guess the construction in classical terms of this spectrum this way was due to Seagal. And now we can do exactly the same thing for forms and get a Grothendieck spectrum. So similar way we do, in fact, it's so similar that I'm gonna copy paste this definition. Let's see if we can do that. And just add forms. So I do the same thing. So instead of taking finitely generated projective R modules, I take those with a form. And I look at the isomorphisms as morphism. This defines a perfectly fine category, and I do the same procedure. And because the hyperbolic map is in fact defined from a functor, I get a map of spectra for free. Here. Well, I guess I need to know that the functor is additive too, but it is by definition. And so I get two spectra, K-theory and Grothendieck theory, and the hyperbolic map. And now the question is, what is the co-fiber of this map? Okay. And maybe I should say, so this spectrum, this Grothendieck spectrum was constructed by, roughly this way, by Karoubi and Villamayer. Okay, and so question, what is the co-fiber? And the answer of this question is going to help us understand this group, because it turns out that the co-fiber of this hyperbolic map is much simpler than these two. So these are both very difficult to understand. So K-theory is notoriously difficult. This is even more difficult. Well, it turns out that the co-fiber is much simpler. And it's much simpler because it doesn't arise naturally as a group completion, but it arises by a different type of construction. And I would like to spend some time in explaining how that comes up. So what is the co-fiber? And the spectrum, so this will be one of the so-called L-theory spectra. And these are easier and they arise in a different manner. So, which arise. Okay, so let me spend a bit of time now constructing these spectra. And this also gives me a chance to give a higher categorical framework for doing growth inhibit theory as well. So, and here is where my talk actually starts. I'm going to talk about Poincare categories. And L theory. Okay, so let me just dive into it immediately. Definition, this is due to Lurie. A Poincare category is a stable infinity category. Let's call it C. And I mean, the standard example to have in mind is chain complexes over a ring. So typically, so we take the category C to be the bounded derived category over ring R. So what is it? This is, you take chain complexes of bounded length of finitely generated projective R modules, and you form an infinity category by inverting the quasi-isomorphisms. But this is not the homotopy category. You need to localize in the infinity categorical version. Or in other words, you can look at chain complexes and quasi-isomorphisms as a relative category, so a category equipped with a notion of weak equivalence, and then there is always a formal procedure that you can use to obtain an infinity category from that. So this is always the example to have in mind. So this is the infinity category that encodes the homotopy theory of chain complexes. So this is the example. And so Poincare category is such a thing together with a functor Q from the opposite category into spectra. And again, if you really want to have this example in mind only, you can also take a functor valued in chain complexes. That's also fine. That's also fine. Already gives a lot of interesting examples. So it's a functor like this, which satisfies certain conditions. So let me go through them briefly. So the first condition is that this functor is reduced. So it sends the zero object to the zero object. Oops. It is too excisive. Okay, this is in the sense of Goodwillie calculus of functors. And finally, there's a non-degeneracy condition. So satisfies and let me not say exactly what this condition is, but instead let me tell you what you get out of it. So so the non-degeneracy conditions gives rise to a canonical duality So what's a duality? Is a map, is a functor. It's an equivalence of categories from the opposite category to C. And, and not only that, but also a map sorry, from the value of this functor Q at an object into a morphisms from C to the dual of C. Okay, and I mean, I've given a few talks about this, and I usually spend some time in explaining exactly what this condition is, and I don't think it's worth it. So this is really all you use, and I would like to instead use the time to actually go through some examples carefully. And in fact, there's a classification theorem due to Lurie and Goodwillie that says that somehow all of these functors are all constructed by a certain procedure, and this procedure is hopefully going to be clear in the examples we're going to cover. So I'm not going to go into more details about this definition, but instead I'm going to give a bunch of examples in a little bit. But what's the point of this, of having this structure? So the point of this structure is that it somehow encodes a formal notion of forms on the objects of C. So let me write that down. So the idea is the following. So first of all, because of this map, let's give it a name. Let's call it lower sharp. This Poincaré structure, this functor Q, is a refinement of the notion of duality, of the structure of a duality. So this is one way of thinking about it, and this is very similar. If you like equivariant homotopy theory, this is in a very similar manner to how genuine equivariant spectra are refinements of spectra with an evolution. You can think about duality as some sort of evolution on the category, and this Q, because of this map, is a refinement of a duality. And this encodes the notion of forms. So how? Well, and we think of QC as being the spectrum of forms on C, or maybe I should say the infinite loop space of the spectrum is the space of forms. On C. So it's a formal way of associating to an object of C a certain space of forms. Okay, and we take this aspect, we will take this as a step further, and we define the space of forms exactly in this way. So we define the space of Poincaré objects of this category as a certain space consisting of pairs of an object of C and a point in the infinite loop space of QC. So these are all forms, and now we want to say that they are non-degenerate. So, and here is where we use our map sharp. So we ask further that Q lower sharp, which is a map from C to the dual of C, is an equivalence. Okay. So this is analogous to when we defined forms in algebra before, to asking that the adjoint map of a form is an isomorphism from an object to its dual. Okay. So this is, by definition, the space of forms, the space of Poincaré objects. Associated to this Poincaré category. Okay. And now, if you bear with me 2 more minutes, I'm going to define or say something about the L-theory spectrum of such a thing, and then go through our other examples. So let's see, what time is it? Okay. So first, let's see what the analogous of the Witt group is. So but I'm going to change notation slightly. I'm going to call it the L group. So we define L naught of CQ as follows. We look at isomorphism classes of this object. What does it mean? We look at pi 0 of this space. Okay, so this corresponds to isomorphism classes of forms in our category. And then we want to mod out by Lagrangians. So here's the relation. We mod out by, we identify a pair CQ with 0, precisely if, and now I'm going to try to copy the notion of Lagrangian I had before. So if there is a map in my category, a morphism in C, such that so Q is a contravariant functor. So if I have a point Q in QC, I can pull it back to a point in QL, and I call this point the restriction. And I want this to be 0, and I guess homotopic to 0. So the same path component as 0. And moreover, I want a non-degeneracy condition. I want and it's going to be the same as before. I have this map. Again, I can identify this with the dual via my map Q sharp, and then take the dual of this inclusion, which gives me a map to the dual value. And I want this to be, again, by ignoring this identification here, to be 3 terms exact sequence, so a fiber sequence. Let's see. Okay. So this is a notion of Lagrangian, and I can quotient by those forms that emit a Lagrangian. And in fact, we can do better than this. We can build a whole spectrum such that this is its pi naught, and this is the L spectrum, and we build it from, well, let's see. So we can moreover construct a simplicial object. So a simplicial space, it looks a bit like this. So the 0 simplices are going to be given by this space of forms. And then the 1 simplices are going to be given by 2 forms and a cobordism, which is a diagram of the following form. We have the underlying objects, and we look at a diagram like this. And together with, let's call this maps F and G, and together with, we want to say that the forms pull back to the same form on D. So we want an identification of F upper star of Q with G upper star of Q prime. These are the 1 simplices. And now maybe you can see from here already that, well, if you think about it a little bit, you're going to see that pi naught of this space, whatever the higher simplices are, you know, pi naught of a simplicial space is given by the co-equalizer of these 2 maps on pi naught. And so you see, you're going to have pi naught of this. And if you think about it a little bit, if we're taking the co-equalizer of these 2 maps, which project respectively on the 2 objects, you're going to find exactly this Lagrangian definition. It's not completely immediate, but it's not difficult either. Okay, what are the higher simplices? Maybe I should write them down here. Let me give you the next one up. So roughly, instead of looking at diagrams of this form, we're going to look at diagrams of this form. No, I'm going to be vague, but what you have forms on these vertices, and then they're going to pull back to the same elements on the middle of the edges. And then these identifications are going to pull back to homotopic homotopies on the middle term. So you can think of this as being 2 cells into these 3. I'm not going to define this formally. And then you can imagine maybe how it keeps going. So the higher spaces are going to be encoded by, so this is a subdivided 1 simplex. This is a subdivided 2 simplex. And the next one is going to be a subdivided 3 simplex, and so on. And this gives a simplicial space by taking the realization. So realize you get a space L of CQ such that pi naught of L of CQ is the L group. And not only this, but it has the following property. It turns out that if you shift or take the loop space, so take the functor Q goes to spectra and follow it by the loop, this you get something, because the loop is exact, you still get a Poincare structure, and it behaves like this. So if you shift the Poincare structure, is the same as not shifting, but shifting outside the spectrum. And this gives you canonical D-loopings. This gives rise to a spectrum, and then we call it LCQ. And not only a spectrum, but see, you also have a presentation of the homotopy groups. Because if you want to know what pi n of this is going to be the same as pi 0 of the n-fold loops. But by this property, this is pi 0 of the thing with the shifted Poincare structure, and pi naught of anything, we have a presentation which is given by this. Just replace Q with the shifted copy of Q. So this comes together with the presentation. Of its homotopy groups. In this sense, this spectrum is much easier to understand than K-theory and microtiny bit theory, as you know what elements in the homotopy groups are very explicitly, and you can just work with these elements explicitly. And in fact, there is a whole technique introduced by Ranitsky of algebraic surgery that gives you a sort of procedure you can try to apply to simplify the classes in these homotopy groups. And I should say, so this construction in this language is due to Lurie for these Poincare categories, but it follows a blueprint of the L spectra classically introduced by Ranitsky, Quinn, and Wall. I mean, and there's a lot of people I should mention here from all the surgery. All people that study surgery theory, they were looking at these groups already. Different people develop different aspects. But. Okay, so this is the L theory spectrum, and now I promised you some examples. So let's try to do that. So the first examples I'll do to Ranitsky, and here goes. So you take the category of chain complexes over R, this bounded derived category, and you can define a Poincare structure denoted like this. S stands for symmetric, and epsilon is the usual unit idempotent in R that we are carrying around to twist our forms. And what do? We look at HOM from C tensor C. So C is a chain complex. I can take the tensor product with itself over R. This is a new chain complex, and I can look at R linear homomorphism into R. Okay, so this is roughly a chain complex version of the pairings, the notional forms we had in algebra before, right? It was a map from a module tensor itself to R. This is exactly what it is in the land of chain complexes. So now you know that this is an involution that flips the two variables and multiplies by epsilon. Okay, and the chain complex version of saying that the form is invariant is saying that it's a homotopy fixed points for this involution. So this is an involution. We take the homotopy invariance. So this is a Poincare structure. And let's see, its L theory spectrum is Ranitsky's symmetric L theory. Let me write it LS of R. Epsilon, it's Ranitsky L theory. And it's, sorry, symmetric. I don't want to stress that. And more or less by definition, except that the fact that this construction is performed in infinity categories, he does it in Poincare models for chain complexes, but it's roughly the same constructions. So it's really, the construction is the same. we can do exactly the same thing, but instead of taking symmetric forms, we take quadratic forms. What does that mean? Define another one of these. We take the same exact spectrum as above, but we take orbits, homotopy invariants. And this gives rise again to a spectrum that we denote by LQ, and is Ranitzky's quadratic. Yeah. So, and moreover, there is a map from here to here. A norm map, it's a transfer map from homotopy orbits to homotopy fixed points. This is the usual transfer map is in group cohomology. Okay, so and it's called the norm map. I'm mentioning this because I'm going to use it in a second. So this gives us two canonical Poincare structures on the category of modules, one that tries to include some homotopy coherent version of symmetric forms, and the other one, a homotopy coherent version of quadratic forms. Now, the next examples I want to mention is a set of examples that we have studied in our papers, and which are a refinement of the previous ones. So we take the same category, and for every integer, we're going to define a Poincare structure as follows. So we take the symmetric one that we just saw, and there is this norm map from the quadratic one, and we look at the cofiber. The cofiber is called the Tate construction by definition. It's the cofiber of this norm map. Okay, and the idea is to take this Poincare structure and twist it by something that lives over the Tate construction up here. So what is that? Let's see. Okay. So it turns out that this is equivalent to our linear home from C into the Tate construction on R. If you want to, you can regard R as an Eilenberg-MacLane spectrum and take the cofiber of this norm map for R. And now we do something that seems really innocent. What do? We take the same thing here, and maybe I should point out, even if R is just a normal ring, the Tate construction has homotopy groups all over the place, because when you take homotopy orbits, you create a lot of higher homotopy groups in positive degrees and homotopy fixed points in negative degrees, and then you take the cofiber and lots of things happen. So this is complicated in general, the construction of R. And I'm going to do something innocent. I'm going to take the connective cover, N connective cover. Sorry, I need more space. Take the N connective cover of the Tate construction. Okay, and the N connective cover always maps to the underlying spectrum, and I use that map, and then I pull back. So I define a new Poincare structure as a pullback, and I call it greater or equal to N of C. Maybe from this diagram I can kind of forget the norm map. Oops, sorry. Doesn't make any sense. I'm pulling back like this. Now I can sort of forget the norm map for a second. So I define this as the pullback of this. Okay, and now why is this a reasonable thing to do? It turns out that every quadratic functor, so there is this classification theorem of Goodwillie and Lurie that says that every quadratic functor decomposes such a pullback where down here you have sort of the symmetric, the homotopy fixed points of the spectrum induced from the duality. Here you have the Tate construction, and here you have anything at all, as long as it's linear in C, that maps down to the Tate construction. So in fact, this is a very general recipe for producing quadratic functors. It doesn't really come out of nowhere. And why? So what do we get out of this? If you think about how the connective cover map to each other, you get a sequence of these functors. So out of this, you get a sequence that starts with the quadratic one, which is what you get if you take n equal infinity. So if you think about it, what happens if you do n equal infinity? You put, this is infinity, means you put a 0 here. And so what you're doing by pulling back, you're computing the fiber of this map, which is by definition is the quadratic one. And then these all map to each other like this. All the way to the last one, which is this minus infinity. And the minus infinity one, well, taking the connective cover for minus infinity means don't truncate anything. So this map is an equivalence. And therefore, when you put it back, you get an equivalence. So the last one is the same as the symmetric. So this is Q. So we get an infinite family of Poincare structure interpolating between the quadratic and the symmetric one. And a remark is that if 2 is a unit in R, these are all equivalences. The reason being, if 2 is a unit, the state construction is 0. Oops. It was a bit harsh. The state construction is 0, and so is this one. And so doing this pullback doesn't do anything. You just pick up the symmetric one, no matter what n is. And this, in fact, I'm going to try to go over it again in a little bit, but this is the whole reason of why the Hermitian K-theory has been well understood for years when 2 is a unit in R, but not so well when 2 is not a unit. Because there are all of these different type of form types that you can consider on the category of chain complexes. There's another example that I want to discuss before moving on, and it's the following. So also we studied in our paper. So far everything was living over chain complexes, everything was linear. Here's the first nonlinear example. Of course, because we are doing stable infinity categories, we don't really have to work with chain complexes. We can work with modular spectra. So let's work over the sphere spectrum. So let's take the category of compact spectra. And then we try to follow a recipe of trying to define some Poincare structure as a pullback like this. So again, we start from the symmetric version of what over the sphere. Now, let me just spell it out explicitly. We look at the mapping spectrum from X tensor X into S. And now these are tensor product over the sphere, so there's mesh products in usual terms. And again, there is an involution here that flips these two variables, and I take homotopy fixed points. Again, this maps to the same thing with a Tate construction by taking the co-fiber of the norm map. And again, like before, this is equivalent to hom from X into the Tate construction of the sphere. And I'm going to use this same trick as before. I want to just produce something up here that maps to the Tate construction of the sphere. Before I was taking connective colors. Now for the sphere, there is something else I can do. There is a bit more, I don't know, more interesting, maybe it's not the right word, but here's what I do. So we take, instead of taking a connected cover, we take a map. There's a map from the sphere into its state construction, which is what's called the Tate diagonal. Some sort of spectral version of the diagonal map that you have in spaces, you know, from X, you can map diagonally to X cross X. This map doesn't exist in spectra, but it exists if you take the Tate construction on this. And then, I guess for this mesh. And then, since the sphere is the unit, this mesh product doesn't do anything in landing. And now we take the pullback, as we did before. And this gives another example of a Poincare structure, this time on the category of compact spectra. And now let me just mention, for those of you who like equivalent homotopy theory, this is in fact equivalent to taking the spectrum X, take the Hill-Hopkins-Ravalan norm from the trivial group to C2, and take its genuine fixed point spectrum. And this square is nothing but the isotropy separation square of this equivalent spectrum. So this is a construction that comes up in equivalent homotopy theory. And why is it interesting in this context? This U stands for universal. And it's interesting because it co-represents forms. So if you take spectra with this specific Poincare structure into any other Poincare category, so now I'm jumping ahead of myself a little bit, but so these pairs of a category with a Poincare structure define a category themselves that I can take home in that category, and this is equivalent as a space to the space of Poincare objects into CQ. So they co-represent forms. And not only that, but there's also this category of pairs have a symmetric modular structure, and this happens to be the unit for that. So it has very, very nice properties. Okay, and so what's its L theory? Well, its L theory was considered by Weiss and Williams. So L of spectra with this universal structure, this I think was denoted just by L of a point, and was considered by Weiss and Williams into their study of automorphisms of manifolds. And it was used to define these higher signatures of manifolds. So it's something that has come up before. And so it's some sort of L-theoretic version of algebraic K-theory of spaces over a point. Okay, so now that we have done all of this work for L-theory spectra, we have our candidate for the co-fiber. Now let me go back to our exact sequence we had at the beginning and try to recover it using all this machinery of Poincare categories. So section 2, let me go back to this fiber sequence I was trying to get to. So the point of our work is that we define kind of how you can define L-theory spectra for these Poincare categories. You can define also Grothendieck spectra. So we define GW of CQ, let's say a spectrum. And I'm not going to give you the construction, but the way we construct it maybe is not, I mean, we kind of follow a recipe that is already out there. So how do we do it? We adapt Horn, Boston, and Schlichtings Hermitian Q construction. So they have a version of the Q construction for categories with duality, exact categories, and we adapt that to stable infinity categories with a quadratic functor, kind of in the same way that the usual Q construction has been adapted to stable infinity categories by Barwick. So maybe let me say that too. So similar in a manner, similar to Barwick's version of Quillen's-Liu construction. Okay, so the construction is not super important, at least not for the scope of this talk. But once we have this spectrum, here's the first theorem. Is that there is a fiber sequence. So for every CQ, Poincaré category, there is a fiber sequence like this, where here is not quite K-theory, but you need to take K-theory and take, there is an involution on this K-theory spectrum, which is given by sending a module or an object to its dual, which is induced by the fact that we have a Poincaré structure, and we need to take homotopy orbits by that involution. So this is defined, is induced from sending P to the dual of C to the dual of C. Okay. So it depends, it comes from the fact that we have a Poincaré structure, but it depends only on the underlying duality and not really on Q itself. Okay, so we do have this fiber sequence. And so now let's try to get to, I mean, so far these are all abstract objects, and let's try to get to the usual Grothendieck groups of rings that we had at the beginning. So first a remark. So what happens when 2 is invertible? So if 2 is a unit in R, then this was a known sequence, more or less. So let's see. We take CQ to be the category of, again, this perfect category of chain complexes. And then remember, we had all of these Poincaré structures, but when 2 is a unit, they're all equivalent. Let me take the symmetric one. So this is the sequence, a known sequence, where at least maybe not at the level of spectra, but at the level of homotopy groups for sure. What are the terms? So the first term is the K-theory of this derived category. Well, this is the K-theory of R. And so I guess the first, in order to identify the K-theory of this with the K-theory of R, this is the theorem of Gillet and Balthausen. Then the K-theory of a ring can be computed as the K-theory of the chain complexes, the category of chain complexes. Then we have the middle term is the Grothendieck spectrum of this category. Oops, right. So it is, but it's a theorem of Spitzbach.
Artikel angeben, die man nicht haben möchte. Also wir können auch drüber nachdenken, da irgendwie.
So it's a theorem of Spitzbach that this is when 2 is invertible, the Grothendieck groups of this category are the usual Grothendieck groups. So this is Spitzbach. Plus a little bit that compares construction for Poincaré categories to his framework with dualities, but this is maybe not that much. And then the co-fiber is Wranitzky's L-theory. Okay, kind of by definition. And this was known. So this was proved, established by Schlichting. Okay, so really, what we need to see is what happens when fluid is not invertible. And this is where really our work comes in. So the problem is, how do you get to this Grothendieck spectrum when 2 is not a unit? And this is this theorem of Hebestreit and Steiner. So they show that so for a general ring R, the way to obtain the Grothendieck spectrum, as I defined at the beginning, is by looking at a specific Poincaré structure on the category among the sequence I gave before. So this is the Grothendieck spectrum of, remember we had this whole sequence of them, and you take the one for n equals 0, corresponding to the 0 connective cover. And to be fair, as I defined this at the beginning, they were connective because I did them via group completion, so I would have to take a connective cover here. But there is another definition that is also classical that gives a non-connective spectrum, and if you take that definition, then this is true without connective cover. But to be fair, I need to write this. And what is the reason? I mean, this is actually not an easy theorem, but the moral reason is the following. Is that if you take this particular one and you evaluate it, so this is a function of chain complexes, so I can evaluate it as a chain complex given by a given finitely generated projective module that I regard as a chain complex concentrated in degree 0. Okay, the point is that this is some spectrum, and what is the spectrum? Is just the Allenberg-MacLane spectrum of the usual forms, as defined at the very beginning of this talk. On P. Okay, they form an abelian group, and its Allenberg-MacLane spectrum is this one. This is not true, and this is not too difficult to see just from the Poolbeck square. And this is not true if you change this, for example, with minus infinity, which was the symmetric version. So the symmetric version is not going to be true. So somehow this is really the crucial input that makes everything work. Okay, so once we know which Poincaré structure we need to look at for recovering the usual Grothendieck spectrum, we can actually look at what our sequence gives. And then we can work a bit on the co-fiber. So for every R, no matter if 2 is invertible or not, there is a fiber sequence. And so again, the K-theory of R with this homotopy orbits by this involution that takes a module to its dual, the Grothendieck spectrum of R, which is given by this theorem by this Grothendieck spectrum, and the co-fiber is going to be the L-theory spectrum of, again, this category with this weird new quadratic Poincaré structure. And again, I should take also a connective cover here if you work with the de-looping I defined at the beginning. But if you look at, let me not insist on that. Okay, so now this is the fiber sequence which exhibits our usual Grothendieck spectrum as an extension of these two. So now we really need to understand this L theory here. So Ranitzky has computed lots of things about L theory, and we can use his calculations to figure out this spectrum. So let me say a little word about that too. So in fact, pi n of this spectrum here was already considered by Ranitzky and is the original definition of symmetrical theory. Given by Ranitzky. So in his book on algebraic theory of surgery, the first book on foundations, he actually gives a different definition than the usual symmetrical theories groups. And eventually he changes this definition to the newer ones because those happen to be periodic, whereas these are not. But it turns out that this very natural Poincare structure gives rise precisely to these groups. And better yet, we can actually say something about what these groups are. So let me say that too. So if, under a condition, so if R has global dimension, has finite global dimension, D, so meaning every module can be resolved by at most D modules, then these groups here are the symmetric groups in sufficiently high degree. So if the degree is greater or equal to D minus 1, but this is the global dimension, they are the quadratic one in small degrees. So if n is less than or equal to minus 3. And in degree 0 and 1, they are related to even forms, and so we can also describe them. And between degree 0 and D minus 1, if D happens to be greater than 1, they are something else that we don't know. But so in particular for, say, Dedekind rings or Z, in non-negative degrees, these are which has global dimension 1, in non-negative degrees, we have the symmetrical groups. So in particular, so for example, L theory for Z is the usual theory, symmetrical theory of Z in let me say a star for non-negative star. And these have been computed by Hermitian. Okay, in the last couple of minutes, I would like just to have a range of concluding remarks. So first of all, again, I assume that R is commutative. We didn't have to. So there are versions, all of these results. Work for non-commutative R, but you need some extra structure on R to make sense of this notion of form, and also with coefficients. You know, we were always humming into R, but you can take coefficients from line bundle. And even more generally of some version of line bundle for non-commutative rings as well. So this is really no restriction. And second things I want to say is that there's also a version for quadratic forms. So the same sequence we had here, let me try to move it down there. So you can take the category of, you can take the relatively bit spectrum, but instead of starting with the algebraic notion of a symmetric form, you start with an algebraic notion of quadratic form. So let me maybe write a little Q up here. So start with quadratic forms. And then what you get here as the cofiber is now the L groups you get for the Poincare structure greater or equal to 2. Okay, and the funny thing is that this is related to the symmetric one. So and this co-fiber is a fourfold shift of the old one, of the symmetric one. So so of the one we got for the symmetric group. And this is kind of surprising to me. So there is a fiber sequence for quadratic forms, and the co-fiber up to a shift is again the same as the co-fiber we had before. And finally, let me say something about calculations. So as I mentioned before, for the ring of integers, you get a fiber sequence that looks like this, at least in non-negative degrees. Of the usual symmetrical theory, because you have global dimensions 1. So, and from this fiber sequence, but actually not quite directly from this fiber sequence, but from some results you can extract from this, we're able to compute all of the Grothendieck groups of Z, except for some degrees where there is some uncertainty coming from the fact that we don't really know all the algebraic K-theory of Z. So from this, we can compute these Grothendieck groups of Z. For epsilon, I mean, this is an idempotent, so there's only 2 possibilities in Z. There is plus or minus 1, and both the symmetric and the quadratic version up to some degrees, having to do with the fact that we don't completely understand the K-theory of Z. So, and that's related to the Van Diver conjecture. So let me see. Okay, and I'm almost out of time, so I'm just going to mention this briefly. But there are some results about Grothendieck theory that have to do with periodicity. And I mean, I think we already see most of it here with the fact that this type of periodicity result for the co-fiber of this map, and the fact that at least for the infinity and minus infinity case, these spectra are in fact 4 periodic. So you get that the co-fiber of the hyperbolic map has some nice periodicity results, and you can actually, there is a classical result of Karoubi that expresses this using fibers and co-fibers of the hyperbolic and the forgetful map. It only works when 2 is a unit, and we can generalize this to our family of functors for general rings. Although I'm not going to have time to get into it. Okay, I think that's all I wanted to say. Thank you.
Thank you very much for the talk. Thanks. Emanuele, there was a question in the chat earlier in your talk. It was about Maxime Ramsey asking about the role of 2 excitativeness in your definition of a quadratic form. It was already answered by Thomas Nicolaus, but maybe you want to comment on it. So the question was, what is the meaning of 2 excitativeness in your definition?
Yeah, so it's the definition is due to Goodwillie. So you can look at functors as certain cubes. So you look at functors in a cube where every face is a push out to a cube that is Cartesian. So this is the definition. But then there is this classification theorem of Goodwillie for 2 excessive functors that are homogeneous, and a refinement of that by Lurie that tells you that essentially all of these functors are of the following form, and this is really what you actually use in the end of the day. So if you have such a functor that is 2 excessive, this is always of the form, it's always a pullback. Of the following form. Now I'm mixing up my x's and my c's. That's the x, where this is linear, and this one is bilinear symmetric. Okay, And this is why, in all the examples we had pullback squares. We were constructing our functors as pullback squares because they can always be decomposed like this. So as long as you have something that is bilinear symmetric and something linear, you can always construct them and they're all of this form. I hope that answers the question.
Okay, thank you.
Thank you. Thank you.
Emanuele, you gave some results about the integers. What about finite fields?
For finite fields, yeah, this was already, I think, more or less everything about finite fields was known. So this was computed by Fried. So for two invertible, so as far as two is invertible, the Grothendieck theories, the Grothendieck group split into fixed points of K-theory and N-theory, and this was another result. And for characteristic 2, this was computed by Friedlander. So that's also known.
Yeah.
So really I think our results are new for mostly for ring of integers and number fields in this type of things.
Is there any other question or comment?
Do you have any description of Grothendieck groups over polynomial rings in case the characteristic of the base ring is not, so in case 2 is not invertible?
I do not know. We have this type of Schoenstein splitting results. Marcus is on top of those, but I think it's all over the integers maybe. I'm not sure what happens in characteristic 2. Marcus, are you still there?
Do you have any analog of A1 invariance of Grothendieck groups in which 2 is not necessarily invertible?
Okay, so this is Jonathan Harpatz has been working in that direction, and I think the answer is yes, as long as you don't look at this Q0, but you look at the QS. I think that was the trick. So I think the power of this framework is that you have all of these different Poincare structures, and they have different properties. And in fact, this QS, the one that corresponds to minus infinity, is the one that is best behaved. But somehow the Q0 is the one that relates to forms over actual modules. So there is a bit this dichotomy. Yeah, and I think.
So does this mean that you there is no some simple analog of Bass fundamental theorem for these generalized Grothendieck groups, so that you cannot just write short exact sequences?
I don't know exactly which Poincare structure is going to work for those results. I would expect the symmetric one to work, and maybe not the 0 one in general, but I'm not sure.
Okay, so do I understand it correctly that there might be some simple generalization of the classical Bass fundamental theorem results for this group?
Possibly, I think if you care about the classical group, possibly not.
Okay, thank you.
But if someone has something to add, please.
Anybody else?
Also, I'm wondering, so K-theory has a more general version than just for stable infinity categories, where you take Waldhausen infinity categories. Is there a version of that for this Hermitian K-theory?
We haven't worked it out, but I would imagine that you can probably conceive of such a thing. Certainly for the exact infinity categories. I'm not sure for Waldhausen.
Yeah, I mean, Waldhausen is unlikely because, I mean, you have a duality, so somehow the opposite also
so you need some
category with pretty much an exact infinity category then.
Sorry.
And for exact, I think you can define it probably, but then there is this weird thing that, let's see, how does that work? You can define the stabilization of an exact category, and then they have the same K-theory, right? So
right.
I think in the end of the day, probably stable infinity categories are all that you would want.
Okay, see, thank you.
I mean, I think, let me just add, I think somehow basically what Fabian and Wolfgang do is basically the Poincaré version of that in their paper, that result.
Because they need to work with actual modules, and so you need some.
Right, so somehow this is an exact category and it's a filtration. So I think, I mean, they don't say it that way, but I think one could somehow expect that.
Thanks.
Okay, if there is nothing else to be said, thank you very much again for the talk.
Thank you.
So I stop the recording now, and